Hello and good day. Today, we'll be taking you through the design and architecture of our remote weather station data proposal. Let's get started with the introduction. To overcome the operational hurdles of traditional weather monitoring, such as manual data collection, limited scalability, and risk of data loss, this project proposes a remote weather station data platform built on Amazon Web Services, moving away from rigid legacy hardware to an independent cloud architecture that introduces a cost-effective pay-as-you-go model that automatically scales during IoT sensor spikes. Ultimately, the platform creates a secure automated pipeline that ingests real-time weather streams, cleans and archives historical records, and delivers live climate trends to researchers via a web-based dashboard. Let's move on to the problem statements. The first problem statement is harsh and remote deployment. Weather stations operate on isolated, hard to reach environments requiring highly resilient infrastructure that traditional systems cannot provide. The second problem statement is the storage and ingestion bottlenecks. Local data loggers have finite capacity, causing data collection to stall when full, while central servers suffer network bottlenecks from concurrent IoT data streams. The third problem statement is high data loss risk. On-premise setups lack automated redundancy, meaning a single local hardware failure or power outage can cause permanent data loss. Next up is high maintenance overhead. Physical servers demand constant manual interventions, hardware upkeep, and software patching, pulling away focus from the research. Last up is security and integrity vulnerabilities. Securing data over public networks from scratch is highly complex, leaving unencrypted weather data vulnerable to interceptions or tampering. Let's move on to objectives presented by Kai.
The first objective is real-time data ingestion. Establish a secure, always-on at the Amazon Web Services gateway to continuously collect sensor telemetry from isolated regions over low bandwidth networks. Second, tier and secure cloud storage. Protect scientific data integrity using robust encryption while organizing records into structured and unstructured tiers. Third, instant dashboard visualization. Eliminate manual data extraction by connecting storage layers to an interactive web engine for live browsing-based monitoring. Fourth, automated threshold alerting. Implement proactive safety features that instantly broadcast email notification to emergency teams during severe weather breaches. Fifth, long-term climate analysis. Archive massive volumes of historical records safely, enabling deep analytical queries over months or years without degrading active system performance. Last is serverless scalability and high availability. Leverage a independent Amazon Web Services architecture to automatically handle traffic spikes and maintain 24/7 uptime without manual server management. Next slide will be presented by Jensen.
Scopes. Environmental metric monitor. Temperature and humidity. Tracks ambient thermal values and relative moisture percentage to map localized microclimates. Rainfall and wind speed. Measures precipitation accumulation and air velocity to provide early warnings for flash flood and high wind hazards. Cloud platform capabilities. Tiered cloud storage. Securely archives raw historical records in cost-effective object storage, alongside a structured database for device registry data. Real-time dashboards. Connects the active data pipeline to a visualization engine for live updating charts and graphs. Automated email alerts. Instantly pushes emergency notifications to stakeholders the moment sensor thresholds are breached. Historical data analysis. Preserves long-term chronological data sets, allowing the researchers to query and extract climate trends seamlessly. I'll pass the next section on to Arish.
Now, moving to proposed system architecture, the proposed system architecture is designed to be fully independent, serverless, and event-driven. By eliminating the need to maintain persistent virtual servers, the platform guarantees high availability, automated scalability during severe weather events, and low operational overhead. Let's move on to the services used to make the proposed system. First up is AWS IoT Core. The purpose of using AWS IoT Core is that it acts as a secure cloud gateway to connect remote weather sensors and ingest incoming data streams. For example, a remote weather station in a forest transmits a lightweight JSON packet containing temperature and wind speed values every 60 seconds over a cellular network to AWS IoT cores. The justification behind using AWS IoT Core is that it eliminates the need to maintain a 24/7 listening server. It automatically scales to support concurrent station connections, and natively handle low bandwidth MQTT protocols. Next up is AWS Lambda. The purpose behind using AWS Lambda is it runs backend validation codes automatically on incoming data sets without needing permanent servers. For example, the moment data enters AWS IoT Core, Lambda triggers a quick script to verify and check that the temperature reading is realistic before saving it. The justification is it is fully event-driven and serverless. You only pay for the exact milliseconds the validation code runs, completely removing the idle server cost. Third up is Amazon Relational Database Services, also known as Amazon RDS. The purpose of using Amazon RDS is it manages highly structured relational asset metadata and platform user credentials. For example, storing an organized table of weather station hardware IDs, deployment coordinates, device model numbers, hardware maintenance schedules, and researcher login credentials. Justification. Relational database enforce strict data integrity through SQL schemas, making it simple to run complex queries cross-referencing which technician is assigned to service a specific weather station hardware. Moving up with the Amazon SNS, it will be presented by George.
Moving on to next, the fourth Amazon services that we propose is Amazon Simple Notification Service, which is known as Amazon SNS. Purpose of this Amazon service is that it instantly broadcasts automated alerts when weather reading was safe operational threshold. For example, if Lambda detects wind speed exceeding 90 km per hour, it passes an alert to Amazon SNS, which instantly flashes an emergency warning email to meteorologists. It completely removes the complexity of building or managing system email in some kidney servers, delivering urgent alerts with substantial latency. The fifth Amazon service that we propose is Amazon Simple Storage Service, which is known as Amazon. So this purpose is to serve as a highly durable permanent cloud hive for storing years of massive raw historical weather records. For example, millions of raw sensor payloads collected over the past 3 years and stored safely and files inside a central Amazon S3 bucket. It offers nearly infinite storage capacity and industry leading durability at an extremely low cost per gigabyte. The sixth Amazon service that we propose is Amazon DynamoDB. It stores past high frequency time series meteorological data for real-time visualization and low latency querying. For example, storing incoming temperature, relative humidity, wind velocity, and precipitation values indexed by station ID and sorted chronologically based timestamp. It is a fully managed NoSQL database that stores continuous weather metrics in DynamoDB scales horizontally and delivers single-digit millisecond latency, completely bypassing the red bottlenecks of relational system under high frequency link. I'll pass the next part to try to explain about the Amazon QuickSight.
Amazon QuickSight, the purpose of using it because it provides interactive real-time dashboard interface for data visualization and analysis. For example, a researcher logs into a browser portal to look at interactive line charts comparing rainfall metrics over the last 6 months across different stations. The justification is a fully managed business intelligence tool that plugs directly into S3 and RDS, removing the need to manually build or host a custom dashboard website. Next is Amazon CloudWatch. It monitors the overall system health, data traffic, and operational logs of the entire cloud pipeline. Example, CloudWatch tracks if the AWS Lambda function runs into execution errors or charts a sudden drop in incoming data traffic if a weather station goes offline. The justification, it provides centralized log monitoring and real-time alerts for cloud administrators, allowing quick troubleshooting before system issues impact end users. Going on is the AWS Identity and Access Management will be presented by Jensen.
AWS Identity and Access Management, IAM. The purpose. It manages secure access control, authentication, and granular permissions for all AWS resources. For example, granting the AWS Lambda function a specific execution role that allows it to only write data to the S3 bucket and the RDS database while blocking it from altering any other system configurations. The justification. It enforces the core cloud security principle of least privilege, ensuring that even if one component experiences a security anomaly, the rest of the ecosystem remains fully protected. The Amazon Virtual Private Cloud, VPC. The purpose. Provides a logically isolated private virtual network to secure backend storage and database. The example. Placing the Amazon RDS database inside a private subnet, allowing it to only accept internal network queries originating from your authorized AWS Lambda function. Justification. It secures sensitive backend database layers by preventing an external brute force network attack and controlling traffic flows using built-in security group firewall. I'll pass the next section on to George.
Now that we have introduced our core AWS services, let's trace how they work across our secure serverless data pipeline. Our proposed system is designed to be fully independent and event-driven. By eliminating persistent virtual servers, we minimize idle infrastructure costs and ensure that the platform scales automatically during the extreme weather events. The workflow begins at stage one, secure ingestion. Geographically dispersed weather stations broadcast raw JSON metrics over the internet. AWS IoT Core has our secure edge gateway authenticating its physical device via certificates and safely ingesting the data streams over the lightweight MQTT protocol. This instantly triggers stage two, serverless processing. AWS Lambda runs on demand to parse the raw metrics, format the timestamps, and programmatically validate that the weather readings fall within realistic environmental parameters. During validation, we initiate stage three, automated alerting. If any past metric crosses a defined safety boundary, such as wind speed exceeding 90 kilometers per hour, Lambda immediately triggers Amazon SNS to instantly broadcast critical emergency email alerts to on-duty meteorologists and emergency responders. For normal data, we move to stage four, tiered storage and network isolation. To minimize performance and cost, we divide our data into three specialized tiers. First, validation payloads are written to Amazon S3 for highly durable lost cost archiving. Second, past vendor metrics are stored in Amazon DynamoDB to ensure rapid single-digit millisecond latency for live dashboard queries. Third, structured registry data is stored in Amazon LDS inside a private subnet of our custom Amazon VPC, making it completely invisible to the public internet. Lambda communicates with this private database securely using an elastic network interface, keeping our administrative metadata entirely off the public web. Finally, in stage five, analytic and visualization. Amazon QuickSight connects to our private database just over secure VPC endpoints. QuickSight generate interactive real-time dashboards, historical trend lines, and geospatial uh, map overlays for environmental researchers. Here are the limitations of our proposed system. One of the limitations is that the Lambda code stops. Initial payload after periods of inactivity experience a brief latency delay due to container instantiation, making it less ideal for sub-millisecond real-time tasks. Second limitation would be network dependency. The pipeline depends entirely on remote cellular or internet connectivity. Nuclear tower damage during severe storms will halt data transmission to AWS IoT core. Third limitation, QuickSight visual campaigns. Using Amazon QuickSight with Quick's front-end default customization, binding the user interface, fonts, and rendering to native AWS layouts. Fourth limitation, cost spikes from traffic anomalies. Because serverless services automatically scale horizontally on demand, a non-functioning or compromised sensor flooding the pipeline with duplicate tables can cause unexpected billing spikes. I'll pass to Arif to conclude our presentation.
Thank you, George. So, in conclusion, the proposed cloud platform replaces costly, rigid on-premise infrastructure with an independent AWS serverless architecture that scales automatically during severe weather events. By utilizing AWS IoT Core and Lambda for on-demand data ingestions, a hybrid storage model combining AWS RDS and S3, and built-in services like SNS and QuickSight for instant altering and analytics, the system successfully eliminates custom front-end development and physical server management. Secured via strict IAM access control, this resilient data pipeline can be deployed within an 8-week timeline to fully support long-term climate analysis and critical disaster preventions. That brings us to the end of our presentation. Thank you so much for listening. I hope this presentation helped you understand our proposal. Have a good day.